be revisiting tangent lines, but instead of using tables to evaluate them, we're going to focus on evaluating them using limit laws, or evaluating limits algebraically. So first we're going to look at the curve y equals x squared and the point 1, 1. I'm sure you're having deja vu. But we want to find the tangent line here. So I'm going to start by finding the slope. And we want to find the slope between the point x comma x squared, so some generic point on this graph, which is really just x comma f of x, but since this happens to be the curve x squared, it's x comma x squared, and the point 1, 1. So I'm going to start by finding the slope here. And our slope is the change in y's over change in x. So this is the slope between some generic point on my graph and 1, 1. Now, as I take that point closer and closer to 1, or I find the limit, and as x approaches 1, of x squared minus 1 over x minus 1. Now, when we first did this problem, we can finish this off by making a table of values closer and closer to 1 on either side, and then found the slope. This time, I'm going to do it algebraically. So what I notice when I look at this, I can use the strategy of factor and reduce. Factor to x minus 1, x plus 1 on the top, and I have x minus 1 on the bottom, and now I can cancel out those x minus 1s. So I end up with the limit as x approaches 1 of the quantity, which is just a stray mark, the quantity x plus 1. I can do my direct substitution, and I have 1 plus 1, which is 2. Way faster than writing the whole table out. Then I want the equation. We're going to get y equals 2 x minus 1 plus 1 in point slope form. Alternatively, you could always have it with the k on the other side as well. Okay? So what we've done here is we found the tangent, the slope of the tangent line by doing the limit as x approaches a of f of x minus f of a over x minus a. Okay, and what we're doing here is we have some point here, which is our generic point, x comma f of x, and the value that we're looking for the tangent line at. And we are basically taking the limit as this point, q, approaches the point p. So let's do another one with y equals x cubed and the point negative 2, negative 8. Well, we're going to have the point x comma x cubed, and then the point negative 2, negative 8. So we'll have our slope will be x cubed minus negative 8 over x minus negative 2. Now those two negatives will become positives. And we're going to do the limit as x approaches negative 2. Again, we've seen this problem before, but we did it last time with tables. Now what I'm going to do is do it algebraically with a factor and reduce. So I factored with the sum of cubes, good old algebra 2 throwback. Cancel out the x plus 2's. I'm doing the limit as x approaches negative 2 of the quantity x squared minus 2x plus 4. Now I can do a direct substitution because I don't have any divide by 0 problems anymore. And I get m is equal to negative 2 squared minus 2 times negative 2 plus 4. I get 4 plus 4 plus 4, which is 12. Now my line will be y plus 8 is 12 x plus 2. 12 times the quantity. It's supposed to. Okay. Another way we could do the same thing is using what's called the difference quotient. And then we do the limit as h approaches 0 of f of a plus h minus f of a, all divided by h. And in the denominator, really what you're doing is you're doing a plus h minus a, but the a's cancel. So we usually just write it just as h in the denominator. And what that's saying is, if I have this point of tangency that I want, I can take another point that's h units away and find out that's what this f of a plus h, our unit here, difference between the consecutive points is h. That's why we call it a difference quotient. Okay. So we're going to use the difference quotient this time to find an equation of a tangent line to the hyperbola y equals 2 divided by x at the point 1, 2. So again, that difference quotient that we're working with is the limit as h approaches 0 of f of a plus h minus f of a, all divided by h. It's just another way of doing the slope. So the limit as h approaches 0. For this problem, we're going to be taking our a is going to be 1, because that's the x value of the point of tangency. So we're going to have f of 1 plus h minus f of 1 all over h. So my function is 2 divided by x. So we want the limit as h approaches 0, 2 divided by 1 plus h minus 2. 2 divided by 1 is 2, all over h. Now again, we have another one of our types of algebraic simplifying. Here we have a complex fraction. So I'm going to multiply the top by 1 plus h and the bottom by another 1 plus h. What that does is it will simplify these fractions within the fractions for me. The limit as h approaches 0 of 2 minus 2 times the quantity 1 plus h all over h 1 plus h. Notice I'm not simplifying the denominator because my goal will be to cancel something out. So we're going to simplify in the numerator, 2 minus 2 minus 2h. Make sure you distribute that negative 2 to both pieces. Move it up higher. And then I have h1 plus h at the bottom. The 2's are going to cancel. I'm left with negative 2h over h1 plus h. These h's can cancel. Negative 2, 1 plus h. Now I can do a direct substitution, plug my 0 in, and I get that my slope is negative 2. My equation is going to be y equals negative 2 times the quantity x minus 1 plus 2. So that's using the difference quotient instead. Find an expression for the slope of the tangent lines at various points for y equals the square root of x. Now this is a little different because I want for various points. So I want something that's going to give me an expression at the end and not just a single value. So I'm still going to use the difference quotient because that's what's new here. And we're using the limit as h approaches 0 of f of a plus h minus f of a all over h. Now instead of plugging in a certain value for my a, I'm going to leave it as the variable a as I solve this one because again I want an expression, I want it to have variables in it, and so that I can evaluate it at all three of these different points instead of doing the same problem 3 times. So I'm going to have the limit as h approaches 0 of the square root of a plus h minus the square root of a all over h. Now here I have one with radicals, so I'm going to multiply by the conjugate to simplify it. A plus h times the square root of a plus h plus the square root of a, and the limit as h approaches 0. When I FOIL the numerator, I'm going to be left with a plus h minus a. In my denominator, I'm going to have h times the quantity, square root of a plus h plus the square root of a. So the limit as h approaches 0 of h over h, the h's are going to cancel. That's removing that 0 over 0, which is why I couldn't do a direct substitution at the beginning. We have 1 over a plus h square root of a. Now I can do a direct substitution with the 0. I'm going to end up with 1 over the square root of a plus the square root of a, which is the same as 1 over the 2 square roots of a. So that's the slope of all of the different tangent values, regardless of what a is. So when a is equal to 1, then my slope is going to be 1/2. When a is equal to 4, then my slope is going to be 1/4. When a is equal to 9, my slope is going to be 1/6. So it's nice to be able to make this variable expression for it in terms of a, because now I can evaluate my slope at any point. We can also use this as an application in velocity and tangents, but I will do that in the next video.